Now let's move on to the problem of fitting. Okay? So fitting is something, your network has some set of parameters, right? So essentially what's happening, it's a function, right? And when you're saying that your input is an image and you're making some predictions, so basically you're trying to learn some function which is performing this transformation from image domain to prediction domain. So essentially it's a function, and that function is something which you are going to learn when you are training your network. Now, fitting is something, when you take your data, so those parameters will make the transformations, right? So a perfect fit is something when you have those weight values which takes those input and make a perfect prediction without any error. Okay. Now, if you have too many parameters, then it will be very easy for your network to actually make those predictions, and that's called overfitting. I will describe that in more detail to make it more clear. So the idea is, if you have too many parameters, it will be easy for you to learn that function. You can easily approximate that, right? And that scenario is overfitting. That's not a good idea to do that. We'll talk about that why. The other extreme is you don't have enough parameters. For example, if you just use one neuron to approximate a very complex function, that's not possible, right? One neuron doesn't have that amount of capability. So in that case, it's called underfitting. It means that you are not able to approximate your function well. Now let's try to visualize like how these overfitting and underfitting looks like. So the other point is, if you use a lot of data, because your gradient steps or that learning process being performed on a lot of samples, which will have a lot of variations, so that actually helps you to avoid this overfitting scenario, even if you're using a lot of parameters. And that's one of the reasons why you need a lot of samples to train your networks, because if you don't do that, your network will easily overfit. Okay, so let's first look at the loss curve and how we can relate like this loss curve with this overfitting problem. Now, again, this is the same loss curve. X-axis is like the training iterations or a number of epochs. This is just showing the loss value. That's the starting point. Now, the blue plot is the loss coming from the training samples. So the samples which are using to actually update your weights. All right. And then we talked about, you had like two other splits. One is called validation and the other is called testing. Testing is something which you never look at. So testing, you just evaluate your model. Okay. But validation is something which you can actually peek through. You can test your model in validation and make corrections to your model. So what you will do is, as you are training your model, you will keep computing loss for the validation as well as the test set. Right? And this loss is actually computed over all the samples in the validation and all the samples in the test. So you can see initially all of three are like the loss is very high, which means the network is bad. But if you keep updating the network weights, you can see like the training loss is actually reducing, which should happen because you're using this loss to actually update those parameters, right? And you're moving in that direction, which will reduce the loss value. So ideally, your training loss should always go down unless your hyperparameters are not correct. Now, if you look carefully at like at these two curves, which are coming from validation and testing, you can see like until some point, they're actually following the same trend, which is reasonable because all the images or all the samples from validation and testing were never seen by this model. Okay, so it should be almost similar for both the sets. And at some point, you can see like the loss is actually increasing. Okay, and you know that like the best model is something like where your loss is minimal. And again, that's questionable. There are variations to that as well. But let's just assume for now that, okay, the lower the loss, the best the model is. So at this point, you can see if you keep training your model, the training loss is further going down, but your testing and your validation loss is actually increasing, which means your model is actually beginning to perform worse on your testing samples, which is not good because eventually you want to test a model on unseen samples, right? So this scenario is not good. And one way to interpret this is, after this point onwards, the network is actually just trying to overfit on the training samples. It's just trying to learn those samples, or it's just trying to minimize the loss value specifically for those samples. So it's not like a generalized learning, because that learning is not being generalized to the testing samples. The loss is increasing there. So usually what we do is, if we see such a point, we say that, okay, this is a point which is like the best network, and you use those weights as model prediction, even though your training loss is actually going down. So we don't care too much about the training loss. We care about the testing and validation loss. Okay, so this is the point when your network starts to overfit. And to avoid this overfitting, we have like different regularization techniques to use. So if you think about, just go back to neural networks and try to understand what this overfitting is. So neural networks, you have the input, you have the weights, you have those edges, right? And those weights are being used to actually transform the input values. Now, if some of your weights are actually too high, if they have very large value, then since the output is nothing but a linear combination using those weights, if one of the weight is too high, then that weight is actually dominating the output. It will control what the output is going to be. Okay. For example, let's say you have 3 different weights, and those weights have value 100, 1, and 1. And then you take the input, you take the linear combination, and let's say your input was again a 3-dimensional vector, which is again has value 1, 1, and 1. So if you take the linear combination, you can see that your output is going to be 102. Now, in whatever way you're going to use that activation 102 in the future layers, you can see that that 102 is controlled by the weight which has value 100. And most likely the other 2 weights are, they don't care, right? So if it's 102, it's 101, or almost similar, right? So that's like one way, like how your network overfits. It tries to learn those kind of weights, which controls the predictions. So to avoid that, what we can do is we can add regularization, and a simple regularization is you try to minimize the values of your weights. You don't allow your values to be like some random numbers. Okay. So before going to like the regularization technique, let's try to first visualize what this data fitting problem is by looking at very, very simple examples. But again, whatever we are discussing, these are simple functions, but you can easily generalize these to complex functions such as neural networks. Now, these dots are your training samples. Okay, so in this case, the training data is just like 2-dimensional coordinates. Okay, so this is the training sample. Now, we want to learn a function which can make predictions about these points. Okay, so as a human being, it's easy for me. I mean, I can see that it seems like it could be like it could be a straight line, right? Going from this direction to this direction. And the function which we learn could be a straight line, right? Or something like this. Or it could be a complex function, something like this, which is trying to go through each and every training sample. Right? So these are 2 different functions, which let's say were learned. Now, if you try to compare the number of parameters in these functions, and again, that relates to like the number of parameters you have in your neural networks. In this case, it's just first order polynomial. Okay, so you don't need you need just 2 values. You need the slope of this curve and the intercept. So it's like 2 parameters to define this function. You can say this neural network, if it is a neural network. In this case, it's like a 9th order polynomial. So you need like that many parameters, right? That will be a very complex equation. But whatever that equation is, it's actually pretty good because it's going through each of these training points. Now, if you try to compute loss of this learned functions, in this case, definitely the loss is not going to be 0, because this is the ground truth. But if you look the network's prediction, it's saying something like this. So there is some difference, right? The small difference between what the ground truth is and what your function learns. And that's true for like most of these points. And they're close to the line, but not completely over the line. So the loss will have some small amount of value. All right. But if you look at this function, which was again learned, a lot of parameters, and it's going through each point, the loss is going to be perfectly 0. Because this curve is actually able to predict each of these training samples pretty accurately. All of these points are lying on this curve. Okay, so this scenario is called overfitting. That's what happens if you pay attention to each and every sample of your training data. And if you have enough, like if you have sufficient amount of parameters, you will be able to do that. So this is called overfitting, and this is, I will say, kind of a perfect fit. This is something what we want. So, okay, so this is like, let's try to understand that from a binary classification point of view. So in this binary classification, we have two different classes, red and blue, all right? And all these dots are actually your training samples, again, shown on two-dimensional space. And these curves here are the functions which you're trying to learn. So in this case, this is underfitting, this is overfitting, and this is just like about right on a perfect fitting. Not a perfect fitting, but it's a good fitting. That's what we want. Now, if you try to analyze this, this is a straight line again, very few parameters, 1 or 2 parameters, right? So you have, it doesn't have the capability to learn like this complex boundary, because what we want is, we want a function which can divide like the red samples from the blue samples. Okay, so it will be curved like this, something like this. So this curve will have slightly more parameters than the straight line. Now, this is something overfitting because what it's trying to do is, it's trying to satisfy the loss function for each and every sample in your training data. It's making no mistake. So for training set, the loss is completely zero, because all the red points are above this curve and all the blue points are below this curve. So loss is perfectly zero. In this case, again, you will have some loss. In this case, you will have a huge amount of loss because you are making errors for a lot of the samples. Red are like below the curve, right? And some blue are on top of this curve. In this case, again, it's not perfect because you can see like some blue dots on top and some red dots on the bottom, right? But if you think about, if you were given like some testing samples, okay, so this kind of function or this kind of curve will actually give you a more reasonable result as compared to this plot, which is overfitting, or this plot, which is kind of underfitting. Okay, so let's try to understand. So this is pretty clear. I mean, it's not working, right? Even for these samples, it's actually failing. So if it's not working for training sample, it's not going to work for testing sample. So let's go through the third one, which is overfitting, because it's working so perfectly on training sample. Now, let's say if you have a red dot, which is at this location, right where my laser pointer is. So it seems like it's coming from the red distribution, right? Because it's close to all of those. But this kind of curve will say, okay, no, it's a blue dot, and the method will fail. So that's why it's not good, because it's trying to, like, you can say, please each and every training samples, which is not good. In this case, you can clearly see the distribution. If you pick any red point like on top of this curve, it's going to be red. And if you pick any point towards the blue, it's going to be blue. The challenging cases will be like the boundary cases, but which is fine. That's like challenging even for humans. Okay, so that's what underfitting and overfitting means. And you should also be now able to understand like how number of parameters actually relates to underfitting and overfitting. Okay, so one easy solution for this is early stopping, which we discussed earlier. You just monitor your loss curve. And if your network is diverging, like for your training samples, so diverging is something when your loss started to like increase. That's called the divergence point. So you can use early stopping, just stop there and use that model. You can use regularization, which means like you try to minimize the weight values. Even in this case, when you will have some weights pretty high, right? That's why you are able to form these like complex curves here. So you try to minimize those weights. That's one way. You can use dropout. We will briefly talk about that. And there are many other ways to avoid these problems. Okay, so we won't cover like all of those. So early stopping, we discussed whenever your network is diverging, the validation loss is increasing, you stop there. So that's called early stopping.